Hi YouTube, it's Miron from the Plasmadynamics and Electric Propulsion Laboratory. It's been a year since you last saw me on this channel, and we're now a third-year PhD student. For first-time viewers of my content, you can check out my last video here, also linked in the video description for more context. To recap, I'm studying plasma waves in electric propulsion devices. As a reminder, plasmas are a particle soup composed of many different types or species of particles: negatively charged electrons, positively charged ions, and neutrals with no charge. These particles can respond to pressure and density gradients just like a regular fluid would, but their behavior is complicated by the presence of electric and magnetic fields, which they themselves create and also respond to. Because of this, a small perturbation in a small group of particles locally can set up a whole chain reaction of oscillations that propagate throughout the entire plasma, i.e. plasma waves. Under the right conditions, these plasma waves can spontaneously grow in amplitude by sapping energy from higher energy species, typically electrons, and also deposit energy into lower energy species, typically ions. Given sufficient energy, these ions can then impact thruster surfaces, blasting off material in a process known as sputtering. And it is this process that limits the lifetimes of electric propulsion devices, such as pole erosion seen in magnetically shielded Hall effect thrusters. Unfortunately, the exact relationship between plasma waves, ion heating, and device erosion isn't fully understood, and this is in large part due to limitations in current low-temperature plasma wave diagnostics. Conventional plasma wave diagnostics work by measuring propagating plasma waves at 2 points in space, typically with 2 electrodes. As plasma waves propagate from one electrode to the other, the 2 probes will measure time-varying signals. But because of the spatial separation of the 2 electrodes, there will be a measurable phase difference between these 2 signals. And you can use this phase difference then to back out the wavelength associated with whatever plasma wave you're measuring. The big problem with this is that with only 2 measurements in space, the issue of aliasing arises. To illustrate aliasing, imagine that you don't know the wavelength of the wave a priori. The time-varying signal that you measure at the 2 probes can be represented by these 2 dots. What sort of wave can you fit to these measurements? Is it this one? Maybe it's this one, or maybe it's this one. Without additional information, it's impossible to know what the true wavelength is, and this is the key limitation of current plasma wave diagnostics. My research over the last year has focused on solving this issue of aliasing by creating an experimental methodology that uses multiple probe spacings and angles to de-alias these measurements. To illustrate the principle of operation of this approach, we go back to our previous example of 2 probes inserted into a propagating plasma wave with an unknown wavelength. The exact wave will be ambiguous with these 2 measurements alone, but with additional measurements, you can start eliminating potential wavelengths and eventually zero in on the true wavelength. Now, this is a simplification. You could, in theory, do this exact same thing by inserting a whole array of probes into your plasma all at once. But probes are inherently perturbative, and the more probes you have, the more perturbative it is, which can mess with your measurements. So using some clever frequency analysis tricks and Bayesian inference, we can actually accomplish this with only 2 probes that can translate and rotate with respect to one another. If you're interested in checking out the finer details of this approach, you can read our papers here. After repeating this de-aliasing process for each frequency, you can start building up a mapping between each frequency and its true wavelength. This mapping is called the plasma dispersion relation, and it can tell you what kinds of plasma conditions are at play in your electric propulsion device. This information is very useful and can be used to improve models, resulting in more accurate simulations of electric propulsion devices across their lifetime. The overall goal of my work here at PEPL is to leverage the insights gained from studying these plasma waves to come up with prescriptive mitigation strategies to actively or passively damp these erosion-inducing waves and hopefully result in longer lifetime electric propulsion devices. If you're interested in following along with my research or the research of my colleagues here at PEPL, please check out our website here, also linked in the video description below. That's all for my update video this year. Hope you learned something. See you next year.